We're going to be working through another batch of trigonometry past paper questions today. So looking at some other different kinds of questions that we didn't cover in the last session. So first one, solve the equation 3 sine squared theta equals 4 cos theta minus 1 from 0 to 360 degrees. So our calculator wants to be in degrees. Okay, remember when we're solving an equation, we want to get it in terms of one trig function so that we can then solve. Problem here is we have both sine and cos, but that sine squared should be ringing a bell because we know that sine squared equals 1 minus cos squared. So we can replace, and when we replace that, then we're in terms of cos. So even as you're reading through the questions, bear this sort of thing in mind. What are my identities? Have them forefront of your mind so that as you're reading, you're seeing them as you get to them, rather than having to think through, oh, what are those identities? Okay, make sure that you're very, very familiar with them. So we've got 3 sine squared theta equals 4 cos theta minus 1. And a little reminder, 0 to 360. So we're going to show full replacement. So 1 minus cos squared theta equals 4 cos theta minus 1. Always worth showing that direct replacement, and then you can multiply in the 3. Now we've got everything, no brackets. We want to pull everyone onto one side so that we can deal with our quadratic a little bit more easily. We would much rather have a happy quadratic. So we bring them onto the right-hand side. 3 cos squared theta plus 4 cos theta minus 1 minus 3, so minus 4. Okay, then the usual approach, we're always going to try first to factorize, and the 3 is prime. So we have a 3 cos theta and something, and then we have a cos theta and something. We're going to be subtracting, we're going to be making a 4, we've got a 4 to play with, 4s and 1s and 2s and 2s. So 4 doesn't get us close and 4 doesn't get us close, so it's going to have to be a 2 and a 2. So if we put in a 2 and a 2, then we have a 2 and a 6, and then we have a subtraction that gives us that 4. So unlike signs, the bigger one is positive, 6 is our positive then, and minus 2. So minus 2 cos theta plus 6 cos theta gives us that plus 4 cos theta. And it is so worth double checking your factorized quadratics and just make sure, did you get it right? Because it's one of those steps where it's now going to knock onto everything else. So be sure that you did it correctly. So from here, we now get cos theta equals 2/3, and we get cos theta equals minus 2, and alarm bells ring because, of course, our cos only goes from minus 1 to 1. So this one is a not valid solution. We can't work with cos theta equals minus 2. We can work with cos theta equals 2/3. Okay, we've got a positive, so we need to bear that in mind. So theta equals cos to the minus 1 of 2/3. So theta equals 48.189. And remember, this is always labeled as your PV. Okay, that's your principal value. It's your answer in the 0 to 90 from cos to the minus 1 of the modulus of K. After your PV comes your cast diagram. Noting the sign of K, positive, working with cos, so we want all, and we want cos. So theta 1 is going to equal 48.2 degrees. Answers to degrees to 1 decimal place. And theta 2 is going to equal 360 minus 48.189. Always better to use an unrounded figure for further calculations. And 360 minus 48 point the nonsense gives us 311.8 degrees. So remember that rounding rule of 3 significant figures, except for angles in degrees to 1 decimal place, unless told otherwise. So if we think about it, working with plain cos, working 0 to 360, we should have two answers, and we've got two answers. So we're ending up now just with a final statement of solutions. Theta equals 48.2 degrees and 311.8 degrees. Clear, straightforward, and obvious. So whenever we're working with quadratic trig, then we remember our manipulations come before we do our PV calculation. Okay, so then we do our PV and then we get our answers. Straightforward. The next question is slightly different. See, the next question we have sine 2x cos 2x. So now we are working with an ax plus phi, ax plus b. Okay, a theta plus phi, however you want to put it around. This now is transformed trig. So here we have to express the equation of all of this in the form tan 2x equals k, where k is a constant, and then we're going to hence solve an equation minus 90 to 90. So remember, when it comes to these things, we've got to keep that transformation stuck together until after we've done our PV and our cost. So for part one, we are just expressing. So we have sine 2x plus 3 cos 2x equals 3 sine 2x minus cos 2x. And we want to get that all the way to tan 2x equals k. So tan, of course, we're adding 2. Tan is sine over cos. So t is s over c. You can write them down in the corner if you want to be reminded of them. Okay, so we want to get rid of this bracket so that we can start getting some division through by cos. So sine 2x plus 3 cos 2x equals 3 sine 2x minus 3 cos 2x. Okay, like ones on either side. So we've got cos's together. Let's bring them all positive. So we have 6 cos 2x equals 3 sine 2x minus sine 2x equals 2 sine 2x. Okay, so now we need to get from sine and cos to tan. So we're aiming for sine over cos. Remember, we're not dividing through here and losing a solution because the cos isn't going to disappear. When we divide through by cos, we're going to get 6 equals 2 sine 2x over cos 2x. So that cos 2x is still there. It didn't run away. Okay, but we can now replace sine 2x over cos 2x by tan. So we get 6 equals 2 tan 2x, divide through by the 2 on the outside here, so 3 equals tan 2x. So we now know that k equals 3. Next step then is to do part 2 of the question, to solve this equation. So we've got tan 2x equals 3. And there is nothing we can do about this 2 until we get rid of the tan. So that's why we must work through our PV and our cost first before we deal with the 2. So 2x equals tan to the minus 1 of 3. Again, this is a positive, so we're not all that worried. We are making a note before we lose the question that we're going minus 90 to 90. Our domain has shifted from what we were working with in the previous question. And it's so important to note that domain because that, of course, affects which answers you're going to give at the end of the day and which answers are relevant to this particular question. So 2x is tan to the minus 1 of 3. So 2x equals 71.565. And this is still PV. Doesn't matter that there's 2x on the other side. It is still PV. Okay, next comes cost, all silver teacups. Okay, tan, and it is positive. So we're looking for all, and we're looking for tan. And here you might say, hold on. but our domain is minus 90 to 90. How are we working with over 180? So whenever we're working with transformed trig, it's really important to get all of these solutions from your original cast, and then you're going to apply your transformations on it. Because remember, we're taking our graph and we're squishing it. So it's going to be a very different situation to that normal plane trig. Okay, so we have 2x1, so our first solution, but we're solving here for 2x, equals our PV, 71.565. So x1 is going to equal that divided by 2, 35.8. Okay, so the other solution from our cast, 2x2 is going to equal 180 plus PV, 71.565. So x2 is going to equal 180 plus 71.565, then all divided by 2, which gives us 125.78. Now this is outside our domain. It's bigger than 90. We're going to think and we're going to wait a moment, because remember the other thing that we're going to do here is we've got to figure out our period and how all that works out. So we get our two solutions from our cast, then we consider our period. So period of tan 2x equals, normal period for tan is 180 divided by a divided by 2, so that equals 90. So the period of the graph that we are working with here is 90 degrees. What we're then going to do is take our answers and we're going to move, okay, by a period. So if we start with x1, we would then get to x3. So 35.8. And now we've got to consider, are we going to add our period or are we going to subtract our period? And here's again where our domain comes in. If we say 35.8 plus our period, so plus 90, well, we're going to go over 90. So we're going to be outside the domain. So we don't even bother. But 35.8 minus 90, now that sounds nicely inside our domain. So x3 is going to equal minus 54.2. x4 we would take off our x2, 125.78. Again, we're going to have to go minus 90 because we're moving towards our domain. So x4 would equal, and here's the magic for tan, 35.8, which we've already got, okay? And so it's very special for tan is that we often get this pattern where we're moving a period, then we're actually jumping onto the next tan. So we can now indicate this one here is a repeat solution, and this one here is outside the domain. Okay, and if we went another one down, another minus 90 on our x3 solution, then again we'd be outside our domain because our domain is just minus 90 to 90. So what we've ended up with is only two solutions within the minus 90 to 90. We've also run out of paper here, so I'm just going to put them at the bottom. So the solutions here are x equals 35.8 degrees or minus 54.2 degrees. Two solutions to that equation. So just to sort of go back a little bit and recap again, when you're working with a quadratic trig, you're going to have all your fun and games at the beginning. So you're going to have a whole lot of fun and games. Then you're going to do your PV and your cast, and then you're effectively solving simple trig. When it comes to transformed trig, you're going to do your PV and your cast, and then you're going to have your fun and games after. So that core of the basic trig, we're getting the PV, looking at the cast diagram, that stays the same, whether you're doing simple trig or quadratic trig or transformed trig. It's all about what happens before or what happens after, depending if you've got quadratic or transformed. Are we happy? Okay, cool. So we have another couple of questions. Sketch on a single diagram the graphs of y equals cos 2 theta and y equals a half from 0 to 2 pi. And we change our calculators to radians. As soon as we see pi, we're working in radians for the whole question. Okay, so sketch on a single diagram. So we're going to do a little rough sketch. Cos theta looks like that, right? From -1 to 1 up to 2 pi. But now cos 2 theta means we're going to fit 2 coses in that 2 pi. So we're going to go down, up, down, up. And now we've got a much more squiggly graph. And that's the end of it. No extra transformations. So we get out our pencil and our ruler. And we attempt to draw straight lines for our axes with our ruler. Okay, and then we get our pen to do our labeling because we're sketching here for marks, so it's got to look a bit pretty. So we have 2 pi, we have pi, we have 0, and we're just drawing plain cos, so it's 1, 2, -1. And then we take our pencil again and we draw our curve. So we're going from 1 all the way down to -1, then all the way back up to 1 in half the normal period. So 1 and down and back up, and my goodness, that's awful. Okay, it does need to look like a cos graph, even though it is squished. Okay, and then we repeat the same thing from pi to 2 pi. Okay, so hopefully yours would look slightly more even than that, but you've got a good idea of what we're working with. So this one, we now label, because this is now y equals cos 2 theta. So our axes are y and theta. The other line they want us to draw is y equals a half. So pencil again, and we need that half, halfway between the 0 and the 1. Oops, we don't want it in yellow, we want it in gray. And then back to our pen. This is y equals a half, and this is a half. So we've got everything now on our sketch. Now they ask us to write down the number of roots of the equation 2 cos 2 theta minus 1 equals 0 in the interval from 0 to 2 pi. Okay, well, this looks remarkably familiar to what we've drawn, but not quite the same, but we can check, okay? Remember, number of roots would be a simultaneous equation. So we can set it up of cos 2 theta equals a half, where they intersect. And if we work the magic, 2 cos 2 theta equals 1, 2 cos 2 theta minus 1 equals 0. So we have confirmed that we're just looking for the number of intersections between the line and the curve that we've drawn. So the number of roots is 1, 2, 3, 4. So therefore, we have 4 roots between 0 and 2 pi. Next question gets more fun because it asks us to use our brain. Deduce the number of roots in the equation 2 cos 2 theta minus 1 equals 0, same equation, in the interval from 10 pi to 20 pi. So, we know that in an interval length of 2 pi, we have 4 roots. Now 10 pi to 20 pi is an interval length of 10 pi. So how many roots? Well, if our interval is 10 divided by 2, so 5 times bigger, then our number of roots must also be 5 times more, because it's like having this 2 pi happening 5 times, because it's completely repetitive. It's always the same. So interval length of 10 pi is 4 times 5 is 20 roots. So 10 pi to 20 pi. So 10 pi less than or equal to theta less than or equal to 20 pi has 20 roots for that same equation. Very funky. Okay, and all dependent on that fact that this graph just keeps on going exactly the same. Doesn't matter how far you go in either direction, the graph remains the same. So we can understand a piece of it and apply that knowledge. One more question, just another reminder on that transformed trig. So we're going to play with all the fun and games after we do PV and cost. So solve the equation sine 2x equals 2 cos 2x from 0 to 180, watching the domain again. Okay, so we also back in degrees. So we have sine 2x equals 2 cos 2x. 0 to 180, calculators are changed. Can't do anything because it's sine and cos. Need to get it into one trig function. So sine 2x over cos 2x equals 2. Then therefore, of course, tan 2x equals 2. It's a day for tan questions. So 2x would equal tan to the minus 1 of 2. 2x is going to equal 63.43. And we're labeling PV, and we're not touching that 2. Remember, we're only going to play after cost. Next comes cost, all silver tea cups. Okay, and we're working with tan, and it's positive. So A and T. Again, you say, but we're working 0 to 180, but I remind you, when you're working with transformed trig, you always want to do all your cost solutions. So what do we get? We get 2x1 is going to equal 63.43, a quadrant PV. So x1 is going to equal 31.7 degrees. 2x2 is going to equal 180 plus 63.43. And here's the magic. X2 is going to equal 180 plus 63.43, all divided by 2, which brings us down to 121.7 degrees. You see the magic? As soon as we apply that transformation, we actually pull this into our domain. So we have to have that second one so that we can pull him in when we do the transformation. So if you're doing quadratic or simple trig, then okay, you can manipulate which ones you want to work with. But if you're doing transformed trig, you must get both those solutions from the cost. So again, as soon as we've got our first two cost solutions, we do our period. Period of tan 2x equals 180 over 2 equals 90, and you should see it already. 121 minus 90 gives us the 31. So if we did an x3 of our x1, we would have 31.7 degrees plus 90. Well, that's going to give us the 121. So this one is a repeat. And our x4 would be 121.7 degrees plus 90. Well, that one is going to be over 180. So this is going to be outside domain. So you're always going to that step of considering my period, reminding myself of my domain, and then looking at what my solutions are. In terms of subtracting our period, we're not going to do this in this one because that would be heading down towards the negatives, and we're already only going to 0. So we're happy then that we've got all our solutions within our domain. It's just the 2 of them. So we can conclude that solutions we have, x equals 31.7 degrees and 121.7 degrees. So 2 solutions in our restricted domain, which also makes sense because we have tan 2x, right? So that means we got 2 tans in a normal period. So instead of having our normal 1 tan in 180, we now have 2 tans in 180. So we're going to get our 2 answers for the question. So a reminder, simple trig, straightforward. Quadratic trig, the plane comes before PV and cast. And transformed trig, plane comes after PV and cast. So if you can keep that straight in your mind, then you have a much better idea of where you're going when you get these trig questions. And it really is one of those topics where the more practice, the better. As you can see, we get repetition. So it's worthwhile doing a whole lot of questions and making sure you complete.